This is part of a presentation I did to secondary school maths teachers in Maths Conf in 2017. So here's some algebra here, system of equations, and it really isn't hard. It's child's play literally, because here's a picture of a 4-year-old in reception solving these equations. Except perhaps it doesn't look like you'd expected, it looks like that instead. So we're going to have a look at what's actually going on there. So the first one is that the equation they solved was 2b plus c equals 5. So they had 2 times the value of a box plus 1 value of the car equals 5. And the next equation, 1 box and 2 cars, or 1 times the value of a box and 2 times the value of a cars equals 7. And they went on to solve those largely by logic rather than trial and improvement, which is very nice to see. One of the types of equations I do with young children is Diophantine equations. What I'm about to demonstrate only works with non-negative integers, but eventually as you become more abstract and leave the manipulatives behind, then these same ideas applies to negative as well. So traditionally, when we do 2x plus 3y equals 20, people probably start off with trial and improvement. So the first kind of thing they'll start with is they'll find that works nicely is obviously 2 times 10 is 20, and then y has to be 0. And then probably some more trial and improvement. They'll then find that 2 times 7 plus 3 times 2 works, and then more trial and improvement there. And what's going on is that every time the x value goes down by 3, the y value increases by 2. I want a way to demonstrate why that is rather than just observing that it is. So we traditionally use, I say traditionally, in modern teaching we use algebra tiles. So 2x means 2 lots of the value of x, and 3y means 3 times the value of y. So in formal maths we talk about the multiplicand, the thing being multiplied. So the thing being multiplied here is the x, and the multiplier is there are 2 of them. And here the thing being multiplied, the multiplicand is y, and the thing they're being multiplied 3 times. However, we can turn all of that on its head if we use Cuisenaire rods. So in these diagrams here, 2 is the thing being multiplied, and x is how many times do I multiply it, and here 3 is the thing being multiplied, and y is how many times do I do that. So what we're going to do now is move over to Mathagon and have a look at how I created this and how we then break down what's going on. So what we have here is we've got an equation 2x plus 3y equals 20, and we're going to generate this table here, but perhaps with a little understanding of why when the number of 2's goes down by 3, the number of 3's has to go up by 2. So I've started with 10 2's equals 20. Now if I make a copy of this down here, that's just pressing C on the keyboard. How many 3's can I bring in? Well, it turns out that I can't get rid of 1, 2 or 2 2's. I have to get rid of 3 2's and in its place bring in 2 3's. So you'll notice that the number of 2's has had to go down by 3, and then to compensate for that the number of 3's goes up by 2, and that's because 3 2's are 6 or 2 3's are 6. Now if we make a copy of the next one and have a look at that, we can now get rid of another 3 2's and replace it with 2 3's. And if we make a copy of this one down here and get rid of another 3 2's and replace that with 2 3's. And so we're beginning to understand why every time the number of 2's goes down, the number of y's has to go up. But as that goes down by 3, that has to go up by 2. So we're beginning to understand why this is. And once you have understood how these Diophantine equations work, you take a lot of the trial and improvement out. In fact, you only have to find a starting value, just one will do, and then you can move in either direction. First of all, just in a positive direction here, so these have to go down and these go up. But it's possible once we move beyond the manipulatives to extend this table in both directions. But this is a great introduction for primary, early secondary school pupils. This isn't hard. This is a picture of what were my year 4 pupils at the time. They're now in year 9, I think, or possibly 10. I lose track these days. And there we were investigating that, and instead of Cuisenaire rods, they were using little number counters they'd made with bits of paper. But they were still tabulating the results and beginning to understand why the table generated was like it was. Not just observing the pattern, but explaining the pattern and being able to articulate that.